Welcome back to the deep dive. Today we are wrestling with a paradox wrapped in one of the most widely used materials on the planet, polyethylene terephthalate, or as, well, you probably know it, polyester.
It really is, isn't it? The unsung monarch of synthetic fibers. And looking at the stack of sources you've curated for this deep dive, it's a full technical breakdown. We're really getting into the weeds on recycled polyester, rPET.
That's right. Our mission today, it's simple but crucial. We're analyzing the science behind rPET, the manufacturing, the technical properties, the testing, and really the future of this fiber.
Yeah, and the central question we're tackling isn't just if recycled fibers can replace virgin ones.
No, it's more than that. It's how close are they really? And what's the advanced science, the stuff that's bridging that quality gap?
Absolutely. And to really appreciate the solution, I think we have to start by acknowledging the sheer scale of the problem and the market dominance of this polymer.
Polyester.
Yeah, polyester. Well, it's synthesized using something called a condensation reaction.
Okay, condensation.
And traditionally, that relies on, petroleum-derived materials.
Right, so non-renewable sources, which is a big part of the issue.
A huge part.
And its market dominance is just staggering. It's largely fueled by single-use consumption, isn't it?
Oh, completely. Our sources confirm that PET bottles alone, just bottles, make up something like 83 to 84% of worldwide PP material demand.
83%, wow.
Yeah. And just the interest for PET packaging materials, that was projected to hit 20 million tons back in 2019. It's massive.
This isn't just some popular material. It's like foundational to our global economy.
It really is. And its unique properties are exactly what make it so successful, in packaging and textiles. But that's also what makes it so problematic environmentally.
Right, the double-edged sword. It's valued for what? High strength.
High strength, incredible durability, great resistance to wear and abrasion, all the things you want.
But that durability comes at a massive cost. The shelf life. It's insane.
It is. It takes, what, an alarming 35 to 42 years just for it to begin to degrade?
35 years? Minimum. That just puts the scale of the waste problem into perspective.
It really does.
Which brings us directly to the urgent, unavoidable need for recycling. When we look at the global environmental figures, the numbers are terrifying.
They are. The sources cited estimates ranging from 4.8 to 12.7 million tons of plastics being released into the marine environment annually.
Million tons every year. That's not just a sustainability challenge. It feels more like a planetary crisis that needs, well, immediate material intervention.
Exactly. And the textile industry, which is the other huge destination for PT, plays a massive, often unseen role in this pollution crisis.
Especially through microplastic contamination, right? Those tiny fibers.
Yes. The microscopic fibers shed during laundering. The figures are stark. Laundering just 5 kilograms of polyester materials, that's like a standard load of laundry,
Yeah.
is reported to emit about 6 million microplastic fibers into marine sources. 6 million from one wash.
Good grief. So polyester fibers are now known as a primary source of contamination in oceans and rivers.
They are major contaminants.
So the core benefit of aggressively pushing towards RPE, recycled polyester, it seems pretty clear.
Absolutely. It uses drastically less petroleum. That's number one.
Yeah.
It significantly reduces greenhouse gas emissions compared to making new polymer.
Okay.
And of course, it minimizes the sheer amount of solid waste piling up in landfills.
Right. But to achieve that, we really need to understand the science behind turning that old, maybe contaminated bottle into a new high-performance fiber.
Precisely. The devil is always in the details, isn't it? Which leads us right into the different recycling methodologies. Because how you recycle it really dictates the final fiber quality.
Okay, methods. I imagine the first and, well, the most fundamental step, even before the plastic touches any machinery, must be sorting. You can't just throw it all in together.
You nailed it. It is the absolute bedrock of the entire process. Before any recycling can begin, plastics have to be identified using that numerical coding system, the SPI code.
Right, the little number in the triangle.
Exactly. And our focus here is laser tight on code number 1, polyethylene terephthalate, the stuff used in beverage bottles, food packaging.
And why is that separation so critical? What happens if other plastics get mixed in?
Oh, it's disaster for quality. Contaminants are the enemy. If even a tiny fraction of, say, HDPE, that's code 2.
Milk jugs and things.
Yeah, or PVC, code 3, or polystyrene, code 6. If any of that gets mixed in, the resulting polymer melt becomes unstable. It might be discolored or brittle. You just ruin the batch.
So you need that pure PET stream.
Imperative.
Mm-hmm.
Once recycled, this rPET is primarily channeled into the textile industry. You see it in fibers for clothing, carpets, pillow filling.
Okay.
But the ultimate goal, the dream really, is a closed loop, taking that clear rPET and returning it directly back to bottle manufacturing.
Bottle to bottle, that's the ideal. Okay, so once we have a clean stream of PET flakes, what are the main ways we convert this waste into a usable polymer? You mentioned different paths.
There are two main roads, really. Mechanical recycling, sometimes called physical recycling, and chemical recycling. And they have very different outcomes for the material's integrity.
Let's start with mechanical recycling then. I understand it's the most common and maybe more energy efficient, sometimes called secondary recycling.
That's correct. It's the more common path. This is the sort of linear process most people picture. You collect the bottles, separate them, purify them.
Wash them, yeah.
Wash them thoroughly, grind them into flakes, shred them, melt them down, form that, melt into little pellets.
Okay, pellets.
And finally, melt those pellets again and spin them into fibers.
Seems straightforward enough. But you mentioned a trade-off.
Yes, and it's a critical one inherent in this path.
Yeah.
Every single time you melt that polymer, the mechanical stress and the heat, it causes deterioration.
Okay, deterioration. What does that look like on a molecular level? What's actually happening?
You get something called chain scission. Basically, the long polymer chains get chopped up into shorter pieces, which reduces the molar mass, the overall strength. You can also see hydrolysis if there's any moisture present during melting.
Which weakens it further.
Exactly. And this often leads to reduced material strength, maybe some brittleness, and sometimes discoloration. Yellowing is common.
So because of this quality hit, the result is often considered downcycling, right?
That's the term, yes. Downcycling means you've taken a very high-quality product, like that clear, structurally perfect water bottle.
And turned it into something less demanding.
Precisely. Something less valuable, maybe a low-grade car part, insulation filler, that sort of thing.
Although you hear upcycling used too, especially in fashion.
Right. And in the textile industry, converting a waste bottle into a high-quality yarn for a performance garment, that is often celebrated as upcycling.
Okay.
But it's important to remember that the underlying mechanical process, the repeated melting, still causes some unavoidable degradation compared to virgin material.
So to avoid that degradation entirely, or at least minimize it, we need to look at the other path. Chemical recycling, also called tertiary recycling.
Exactly. Now we're getting into more complex chemistry.
What's fascinating here, based on the sources, is that the goal of chemical recycling isn't just to reuse, but potentially to hit a molecular reset button, to make something as good as, or maybe even better than, the mechanically recycled stuff.
That is absolutely the dream, and it's scientifically sound.
Yeah.
The chemical approach doesn't just melt and reshape the plastic. It actually breaks the polymers down.
How far down?
Back into their basic chemical building blocks. The monomers, or maybe short chains called oligomers.
Ah, okay. Back to the starting material.
Pretty much.
Yeah.
Once you have these basic building blocks, you can essentially repolymerize them, build them back up into a polymer structure that can be indistinguishable from new virgin material.
Right. So you bypass the degradation caused by just melting the old chains. Give us the prime example of this chemical process the source is focused on.
The main one discussed is glycolysis.
Glycolysis, okay.
This process involves something called transesterification, using glycols. Usually it's done under high heat, somewhere between 180 and 250 degrees Celsius.
It's pretty hot.
Yeah. And this is where the magic happens, chemically speaking. Breaking down those long PET chains back into their components, primarily vPET monomer.
And I remember reading this process relies heavily on specific, powerful catalysts. Sounds like another layer of complexity and cost.
It certainly is. Researchers have explored a whole range of catalysts to make this efficient. Various metal salts are common.
Like what?
Zinc acetate is a popular one. It's noted in the sources for yielding the maximum recovery of that vPET monomer, especially in a specific temperature sweet spot, around 180 to 195 degrees Celsius.
Interesting. Any others?
Yeah, other materials like hydrotelsite and even ionic liquids are being explored and used to optimize the speed and, crucially, the purity of the breakdown process.
Purity is key again.
Always. But the major non-negotiable advantage of this complex chemical process is the potential quality. You can yield truly high-quality material, real virgin stuff that can be fully reprocessed without the quality compromises you get from repeated mechanical melting.
So whether you're going down the mechanical route or the more complex chemical one, both paths seem immediately endangered by the same two factors you mentioned earlier: contaminants and moisture.
They are the twin saboteurs of quality RPE production. Absolutely.
For it.
We talked about the visible contaminants, bits of other plastics, colorants, adhesives, especially PVC, which is a nightmare contaminant.
Right, causes structural weaknesses, discoloration.
All of that. But there's also an invisible contaminant that raises a really important public health question: acetaldehyde.
Acetaldehyde. I remember reading that's a toxic compound often released during the thermal phases of peat recycling. Why is it such a major concern, especially if you want to make new bottles?
Because it's volatile and it can migrate. It can easily enter the food chain, particularly if the rPET is being used for new food or beverage containers.
Yeah.
Managing it requires extremely sophisticated control during processing.
So it's a significant environmental and public health risk if not properly mitigated.
Absolutely. And beyond acetaldehyde, the other constant battle is moisture content. Water.
How dry does it need to be?
Incredibly dry. The limit is generally accepted to be below 0.02% water content. That's just 200 parts per million.
Wow, okay. 200 parts per million, that's tiny.
It is. If you have high water content during reprocessing, especially during melting, it immediately triggers what's called hydrolytic degradation.
Hydrolytic meaning water breaking it down.
Exactly. Water molecules attack the polymer chains, causing more chain scission, drastically reducing the material's molecular weight and thus its strength. You basically started degrading the material before you've even finished processing it.
This sounds incredibly challenging. You're dealing with constant heat, sometimes high pressure, precise chemical controls with catalysts, fighting contaminants like acetaldehyde, keeping moisture down to almost nothing.
It is complex. Precision engineering and chemistry.
Okay, here's where the sources introduce something really novel, almost sci-fi sounding. They discuss a different approach, not just for recycling, but for modifying the polymer. Gamma radiation.
Right. This moves us into genuinely advanced material science. Gamma radiation, it's a form of high-energy electromagnetic energy. Most people think of it for sterilization.
Yeah, medical equipment, food sometimes.
Exactly. But researchers are actually using it to precisely modify the physicochemical properties of the polymer structure itself. It's quite amazing.
How does gamma radiation actually work on a plastic chain? What's the mechanism?
Well, it's elegant in a way. The ionizing radiation penetrates the material and produces highly reactive species called free radicals within the polymer chains.
Free radicals, okay. Unstable molecules.
Very reactive. And these free radicals then basically force the polymer chains to react in one of two main ways. Either scission, meaning the chains break apart.
Which you generally don't want.
Usually not, though it can be controlled. Or, more importantly for improving quality, cross-linking.
Cross-linking, so the chains actually join together, form new bonds.
Precisely. They rejoin and form stronger, more ordered, interconnected networks. And if you can control that cross-linking process, you can directly influence and enhance the material's strength and other properties.
That sounds like it has massive advantages over traditional methods that just rely on heat or chemicals.
It does. The sources point out several key benefits. Unlike thermal or chemical methods, gamma radiation typically requires no catalysts. That saves cost and reduces potential chemical residue in the final product.
Okay, no catalyst residue.
Also, it generally needs no thermal activation energy to get started. Polymerization or cross-linking can literally begin at room temperature.
Room temperature, that's a huge energy saving.
It can be. Plus, the reaction is often fast and can be very complete. And crucially, there's typically no emission of volatile organic compounds, VOCs, like residual styrene, which are often problematic pollutants associated with traditional resin curing or chemical processes.
So if I'm understanding this correctly, gamma radiation can help, say, non-cross-linked unsaturated polyester resins reach full polymerization. It takes the liquid resin, maybe from chemical recycling, turns it into a hard, solid form.
Right. Liquid to gel to hard solid.
Improving the cross-linking, enhancing mechanical properties like toughness or stiffness, and making the resulting rPET far more viable for high-stress applications, maybe even composites.
That's the potential, yes. It's a potential game changer for quality control because it allows polymer chemists to effectively engineer the internal structure with a different kind of precision. They can aim to get the polymer chains aligned or cross-linked exactly as needed for maximum strength and stability. It offers a pathway that potentially avoids some of the inherent pollution and contamination challenges of the traditional heat-based or chemical methods.
Fascinating stuff. Okay, so we figured out how to make the fiber either mechanically, chemically, maybe even enhanced with gamma rays. Let's dive into section 3. What are the actual properties of this recycled polyester? The sources suggest it goes well beyond just being, durable.
That's right, and this is where it gets really interesting for engineers and product designers. When the recycling process is managed effectively, particularly using those cleaner, chemically driven routes, or perhaps these novel modification methods, rPET can possess unique, outstanding properties.
So good that it becomes nearly indistinguishable from virgin polyester in terms of strength, durability, versatility, performance.
In many cases, yes. When researchers run comparative tests, they were looking at everything: color consistency, viscosity in the melt, molecular weight distribution, the presence of correct functional groups, and, crucially, thermal properties like melting point and stability.
But here's the bit that really jumped out at me from the notes. The sources mention that in some specific performance criteria, the rPET can actually be superior to the virgin polyester. How is that possible? The waste material is better.
It sounds counterintuitive, doesn't it? But it's a nuance of material science and processing. Certain mechanical properties, like tensile strength, that's how much it resists being pulled apart.
Right, pouring strengths.
And flexibility, or elongation at break. These have been demonstrated in some studies cited to be higher in certain types of rPE fibers compared to some comparable virgin polyesters.
Higher strength from recycled material. Why? What's the explanation?
This unexpected superiority is often attributed to the specific processing conditions used during specialized recycling and, critically, during the fiber spinning stage. It can lead to a more optimized, distributed arrangement and orientation of the polymer chains along the fiber's axis. You essentially create a better internal structure through careful processing of the recycled material.
That's a strong claim. Can you give us a concrete, real-world example of this superior strength the sources provided? Something beyond just textiles.
Sure. Let's look at its use in construction, which is maybe unexpected for PD. The sources cited research focusing on polymer concretes, where rPET flakes were used as an aggregate or reinforcement.
Okay, plastic and concrete.
These rPET-enhanced concretes showed a really impressive compressive strength, about 73.7 megapascals MP, after curing for just 7 days.
73.7 MP. How does that compare to regular concrete?
It's significantly stronger. Standard commercial concrete, like for sidewalks or foundations, might top out around 30 to 40 MP, maybe 50 for higher strength mixes. So 73.7 is quite high performance.
Wow.
They also showed a tensile strength of around 7.85 MPa, which is also good for concrete materials.
So this proves rPE isn't just some eco-friendly filler. It can be a genuine high-performance structural enhancer, even in demanding applications like construction materials.
Exactly. It immediately frames rPET as a potentially high-value technical material, not just an environmental compromise.
Okay, what about physical characteristics relevant to the consumer, especially in clothing? Like how it feels or handles moisture.
Right, the tactile properties.
Yeah.
Molecular arrangement does shift slightly when P is recycled. The sources noted that rPE fibers often exhibit an enhanced moisture regaining capacity compared to virgin P.
Meaning it can absorb and release moisture better, like for sportswear.
Potentially, yes. Better wicking, maybe more comfort in activewear. On the flip side, virgin P tends to have a slightly higher bending length.
Bending length is that stiffness.
It's a measure of stiffness, yes.
Yeah.
So virgin peat might feel a bit stiffer or have more body. This difference is generally attributed to a slightly lessened degree of crystallinity, often found in rPE materials compared to their virgin counterparts.
So maybe marginally softer, drapes differently, but the overall performance is still premium.
That seems to be the conclusion, yes. The fundamental polyester properties remain.
Okay, we established earlier that polyesters are generally flammable. That's a known characteristic. If rPET is being used in applications where safety is critical, cars, buildings, how does its thermal stability and fire resistance compare?
That's a really important point. Polyester, virgin or recycled, is inherently flammable. It will burn. However, its thermal stability and fire resistance characteristics can be dramatically enhanced through innovative modification techniques.
Like adding flame retardants.
Yes, but in sophisticated ways. The sources detailed a process of encapsulating the rPET fibers with advanced materials, specifically mentioning magnesium hydroxide nanocomposites.
Encapsulating, like coating the fibers with these nanocomposites.
Kind of, yes. Integrating them at the nanoscale level. And the tangible benefit of adding this layer, this integrated protection, is critical for safety applications.
How so? What does it improve?
The treated rPET material shows significantly improved fire safety metrics. Things like a prolonged time required for ignition, it takes longer to catch fire, a reduced mass loss rate during burn, it burns slower, and importantly, a decreased rate of smoke production.
Less smoke is huge for safety.
Absolutely. This kind of enhancement moves rPET into applications where fire safety standards are mandatory. Think automotive interiors, aircraft components, public building furnishings, mattresses.
That's impressive. Now, another property I found absolutely fascinating because I never would have guessed it. Acoustics. Using rPET for sound absorption.
Yeah, it's a perfect example of looking beyond the obvious applications like clothes or bottles. Its feasibility for sound absorption comes down to the material's basic properties. It has a low specific gravity, meaning it's lightweight, and it has a fibrous structure.
Which traps sound waves.
Exactly. The porous fibrous network is good at dissipating sound energy. The sources cited a specific study where rPET fibers, when combined with natural wool fibers in a non-woven mat, achieved an effective sound absorption capacity of about 70%. And that was across a really wide frequency range from 50 Hz, which is quite low, all the way up to 5,700 Hz.
70% absorption is pretty good.
It's very effective. And this performance makes these rPET-based acoustic panels a highly preferred choice over panels made from conventional virgin fibers. Not just because of the sustainability angle.
But also cost and handling.
Right. They're often less expensive and easier to handle and install due to being lightweight. Think office partitions, wall panels, automotive sound dampening.
So we've established rPET can be purified chemically, its structure can be enhanced, maybe even with gamma rays, and its final properties are often excellent, sometimes even superior. But the real proof, the industrial acid test, is simulating actual production. Let's shift focus to Section 4, the cutting-edge melt spinning, where researchers put rPET head-to-head against virgin material in a factory-like setting.
Yes, this specific research comparison we looked at is really the backbone of the argument that rPET isn't just good enough, but a genuine technical breakthrough for fiber production. The goal was explicitly to simulate what happens in a large-scale spinning factory.
And they compared different types of PT.
They did. They took two types of recycled PT flakes derived from bottles. One was a mixed colored batch, let's call it rPT. The other was a clear, presumably higher purity batch, rPTB.
Okay, mixed versus clear recycled. And they tested these against virgin PT.
Against three distinct types of virgin PT granules.
Oh.
Let's call them VPT1, VPT2, and VPET3. These varied in their properties, like molar mass or intrinsic viscosity, representing different grades available commercially. One was specifically a fiber-grade virgin material.
And they used highly controlled industrial-style machinery to spin fibers from all these. Specifically, melt spinning with the capillary rheometer you mentioned.
That's right. The melt spinning process is fundamentally about forcing molten polymer through tiny holes, like a shower head, to create continuous filaments or fibers. They used a capillary rheometer.
Which measures how the melt flows.
Exactly. Its viscosity and flow behavior under pressure. And they combine this with an air aspirator. This uses airflow for aerodynamic stretching of the freshly spun fibers.
Stretching them while they're still hot and soft.
Precisely. This setup allowed them to carefully control the take-up pressure, essentially how fast the fiber is being pulled away and stretched as it cools. They tested this across a range from 0.5 up to 3.0 bar.
And controlling that pressure, that stretching, is critical for the final fiber properties, like strength and fineness.
Absolutely critical. Higher stretching generally leads to more molecular alignment, thinner fibers, and potentially higher strength up to a point.
So what were the key findings? Which materials actually behaved well under this high-stress industrial simulation? Which ones could be spun effectively at high pressures?
The results were quite definitive, and maybe a bit surprising. The high-purity, clear recycled flakes, the rPTB, and one of the virgin materials, the standard fiber-grade homopolymer, VPT12, these two yielded the optimal spinability.
What does optimal spinability mean in practice?
It means they maintained a very stable melt flow, even at higher pressures. They didn't break easily, and they produced fibers with a very uniform diameter distribution. That's indicated by a low standard deviation in fiber thickness.
And that uniformity is good for making yarn later.
Essential. Uniform fibers mean fewer breakages during spinning and weaving, and a higher quality final fabric.
Okay, so the good recycled stuff performed as well as the standard virgin fiber grade. What material failed the stress test? Was it the other recycled batch?
Interestingly, no. The material that really struggled under pressure was actually one of the virgin materials, VPT33. This was the one with the highest initial molar mass.
The supposedly strongest virgin material.
You'd think so, but it showed poor flowability and melt instability, especially at higher pressures. The fibers it produced had a rough surface texture. Its viable maximum take-up pressure was limited to just 2.0 bar when spun at 270 degrees Celsius. Any higher, and it just wouldn't spin properly.
So just being virgin and having high molecular weight doesn't automatically guarantee good processing performance. The specific polymer architecture matters.
Exactly. It really underscores the importance of matching the polymer grade to the process, whether it's virgin or recycled.
But contamination clearly still caused problems on the recycled side, even in this controlled study.
Oh, definitely.
Yeah.
The study carefully tracked molar mass degradation. Remember, that's the measure of how much the polymer chains broke down during melting and spinning.
Right, chain scission.
And the mixed multicolored flake blend, the rPTA, suffered by far the highest molar mass loss, up to a staggering 30.0% loss in some conditions.
30%. Why so high?
The researchers directly attributed this severe degradation to the unavoidable contaminants present in that mixed color waste stream. Things like different dyes, maybe residual labels, other plastics, they just accelerate breakdown under heat.
Makes sense.
They also noted a general trend. Copolyesters, which included both the recycled flakes, rPETA and rPETB, as bottles often use copolymers for clarity, and one of the virgin grades, vPET2, tended to show more thermal degradation than the simpler homopolyesters, like vPET1 and vPET3.
Why would copolymers degrade more?
Likely due to their slightly lower melting temperatures and perhaps less stable chemical structures compared to homopolymers.
Okay, let's sit back from the technical details for a second. If you had to give the single most important takeaway from this melt spinning study, the bottom line, what would it be?
The bottom line, the real breakthrough demonstrated here is this. The study proved it's entirely possible to produce PET fibers from bottle-grade recycled copolymer PT, the clear rPTB, that possess properties like desirable tenacity, strength, outstanding elongation at break, stretch, and excellent fineness, thinness, that are similar to fibers produced from the standard fiber-grade virgin homopolymer PT, vPET1.
That is huge. It's basically saying high-performance substitution is technically possible right now using existing waste streams if they're clean enough.
That's the implication, yes.
But I'm still chewing on one detail we touched on earlier regarding the properties. How did the recycled rPETB achieve essentially the same strength as the virgin vPET1 if the rPET inherently had less crystallinity, as you mentioned? That sounds like two different internal structures achieving the same result.
It is precisely two different microstructural solutions, and this is where the subtle material science gets really fascinating and important for processing. A fiber's mechanical strength ultimately depends on two main factors at the molecular level.
Oh yeah, what are they?
One is crystallinity. That's how neat and ordered the internal structure is, how tightly packed the polymer chains are in crystalline regions. The other is molecular chain orientation. That's how aligned the individual polymer chains are along the direction of the fiber axis.
Like logs floating down a river, all pointing the same way.
That's a great analogy. High orientation means the chains are stretched out and aligned parallel to the fiber length. High crystallinity means they're also packed closely together in an ordered way.
So what path did the successful recycled material rPETB take to achieve its strength? Was it crystallinity or orientation?
The rPTB achieved its strength primarily through high molecular chain orientation. When they analyzed the fibers spun at high pressure, they found evidence of very high alignment. One indicator they used was the shrinkage ratio, which was very high at 51.6%.
High shrinkage means high orientation.
Generally, yes. It indicates the chains were really stretched out during spinning and want to relax back, but its measured crystallinity was relatively low, only about 11.4%. So its strength came mostly from the molecules being tightly pulled into those parallel lines, like your log.
Okay, so rPETB strong due to orientation. What about the virgin vPET1 it was compared to? How did it get its strength?
The vPT1 achieved its comparable strength via a more balanced combination.
Yeah.
It had decent molecular orientation. Its shrinkage ratio was lower, 39.3%.
Right.
But it had significantly higher crystallinity. XC measured at 17.2%.
So the recycled stuff was strong because it was pulled, taut, and aligned, while the virgin stuff was strong because it was inherently more organized and packed internally.
Exactly. Two different routes to the same mechanical performance endpoint. And understand this is gold for process engineers. It tells them they can potentially tune the spinning parameters, like take-up speed and temperature, to optimize either orientation or crystallinity, depending on the input material, virgin or recycled, to hit the target strength.
That's really clever. I noticed the sources then jumped into predictive modeling, using things like Weibull distribution plots. That sounds like a level of statistical rigor aimed squarely at convincing industry engineers, not just publishing a paper.
That's exactly right. For industry adoption, especially for something like replacing virgin material, you need robust data and statistical reliability. They used Weibull distribution plots. These are standard engineering tools used across many fields to analyze failure data and assess the statistical reliability of a material's properties, like its breaking strength.
So predicting the probability of failure.
Essentially, yes, assessing the consistency and reliability of the strength. And they went even further. The researchers developed, apparently for the first time in this context, a new semi-empirical power law equation.
Okay, math alert. What does this equation do?
You don't need to memorize the equation, but what it does is relate two key performance metrics: the characteristic tenacity at T0, which is like the representative strength, and the characteristic elongation at break, the representative stretchiness.
And why is relating those useful?
Because it provides essential guidance for optimizing the process. It creates a predictive model. It gives manufacturers a tool to estimate how changes in processing might affect both strength and stretch simultaneously, based on the quality of the recycled input. It helps them navigate the trade-offs and dial in the process more efficiently.
So it moves beyond trial and error, provides a quantitative guide.
Precisely. It builds technical credibility and offers practical tools for implementation.
And this analytical rigor, this need for proof and prediction, is absolutely critical for giving rPE the technical standing it needs, which leads us perfectly into Section V, testing and identification. How do we actually test and identify recycled polyester once it's out of the research lab and circulating in the complex global supply chain to ensure it is recycled and it does perform?
This is mission critical. To meet global demand, satisfy regulations, and maintain consumer confidence, producers and brands must be able to verify two fundamental things about their polyester.
What are they?
First, that the fiber or product has, in fact, been made from recycled material, and ideally to what percentage, pre-consumer versus post-consumer. Second, that this recycled material possesses the necessary molecular integrity and purity required for its intended end use.
So you're measuring everything from its history to its future performance.
Pretty much. We need ways to accurately measure things like molecular weight, crystallinity, the level and type of any contamination, and its thermal stability.
Okay, let's start with the most fundamental check, the one that tells you if the material has been degraded, if those chains got chopped up during recycling.
That would be the intrinsic viscosity, or IV value. This is probably the single most widely used proxy for molecular weight in the polyester industry.
Proxy for molecular weight, meaning it tells you how long the polymer chains are, roughly.
Exactly. Higher 4 generally means longer chains, which correlates to better mechanical properties like strength and toughness. If the chains are shorter, lower feet, the material is likely weaker.
What's a typical 5E range for good quality fibers?
For high-quality fiber-grade textiles, the IV typically needs to be in the range of about 0.40 to 0.70 deciliters per gram, DLG. If testing shows an IV dipping much below that, it indicates significant degradation or chain scission might have occurred during recycling. You likely have a weaker product.
Okay, IV checks the chain length. How do we check the physical structure, the shape, the surface of the fiber itself?
For that, we primarily use microscopy, specifically scanning electron microscopy, or SIM.
SIM, like super high magnification photography.
Essentially, yes.
Yeah.
Think of it as forensic photography for the fiber.
Yeah.
SIM lets you examine the fiber surface in incredible detail. You can look for defects, roughness, inconsistencies, or even tiny contaminants stuck to the surface.
And you can see the shape too.
Yes, and that's crucial. You can check the fiber's cross-section. Regular commodity PE fiber is usually round, but many high-performance textiles use specialized cross-section shapes, things like trilobal, Y-shaped, T-shaped, or even hollow cores.
Why the different shapes?
They're engineered for specific functions. Trilobal shapes can give better luster or soil hiding. Hollow cores trap air for thermal insulation, making fabrics warmer. T-shapes might help with moisture wicking. SEM is vital to ensure the integrity of these specialized cross-sections wasn't damaged or distorted during the recycling and respinning process.
Makes sense. Okay, then we get into the heavy hitters of chemical analysis spectroscopy, techniques that tell you the story of the molecules inside the fiber.
Precisely. Spectroscopy is about interacting light with the material to understand its chemical makeup. Two common workhorses here are Raman spectroscopy and Fourier transform infrared spectroscopy, or FTIR.
Raman and FTIR, what do they tell you?
They both shine light, laser for Raman, infrared for FTIR, onto the material, and based on how that light scatters or is absorbed by the molecular bonds, you get a unique chemical fingerprint or spectrum.
A fingerprint for polyester.
Exactly. These methods are excellent for rapid molecular identification, confirming, yes, this is polyester. They can also provide information about density, the degree of crystallinity, and verifying the presence of specific chemical functional groups. For instance, they can easily identify the signature benzene ring structure that's inherent to peat, confirming its chemical identity and purity.
Okay, so Raman and FTIR give you the chemical fingerprint. But if you need an even deeper level of detail about the chemical structure, its environment, maybe even its processing history, what tool do the researchers pull out then?
For the deepest dive into molecular structure and dynamics, you often need nuclear magnetic resonance spectroscopy, or NMR.
NMR, that sounds serious.
It's a very powerful technique.
Mm.
If FTIR is the fingerprint, you could think of NMR as the detailed molecular biography. It examines the nuclei of atoms within the molecules, providing incredibly rich information about the physical state, the precise chemical structure, and other structural details.
Like what kind of details?
Analysts can use NMR to track subtle changes related to internal processes. For example, confirming the exact degree and type of crystallization, understanding the effects of spinning conditions, or even verifying the finishing treatments that were applied to the textile material. This level of detail is crucial for verifying high-value, high-performance textiles.
Okay, moving from chemistry to heat. Thermal analysis. This seems essential for ensuring the material won't, melt or degrade unexpectedly when it gets hot, either in use or during manufacturing.
Absolutely critical. The two main techniques here are thermogravimetry analysis, TGA, and differential scanning calorimetry, DSC.
TGA and DSC. Let's start with TGA. What's that measure?
TGA is basically a thermal endurance test. You place a tiny sample of material on a highly sensitive balance inside a furnace, and you heat it up steadily while continuously measuring its weight.
So you see when it starts to break down and lose mass.
Exactly. TGA determines the temperature at which the material starts to decompose and lose weight, telling you its overall thermal stability. For instance, remember that contaminated recycled batch, rPTA, from the spinning study?
Yeah, the one that degraded badly.
Its TGA curve showed it had the lowest decomposition temperature, starting to break down significantly around just 365 degrees Celsius. That low value signaled its inherent weakness and instability compared to the cleaner rPET or the virgin materials.
Okay, so TGA checks the decomposition point. What about DSC? Differential scanning calorimetry.
DSC measures heat flow into or out of a sample as its temperatures changed. It's incredibly sensitive to thermal events like melting or crystallization.
So it detects phase changes?
Yes. As you heat the sample, DSC detects endothermic effects, where the material absorbs heat that typically corresponds to melting. And as you cool it, it detects exothermic effects, where the material releases heat that usually corresponds to crystallization.
And what key information does this give you for rPET?
It allows analysts to estimate two critical temperatures. First, the crystallization temperature, TC, where the polymer chains organize upon cooling. Second, and arguably more important, the melting temperature, TM, which for most PE falls in the range of 250 to 260 degrees Celsius. Knowing these points precisely is vital for controlling the spinning and heat-setting processes in textile manufacturing.
Got it. So we've measured chain length, fiber shape, SEM, chemical identity, FT Raman, molecular details, NMR, and heat behavior, DGA-DSC. What about the precise distribution of molecular sizes? You mentioned chain scission chops up chains. Does it chop them all evenly? Why is the distribution important?
That's an excellent question. Now, degradation processes like chain scission rarely happen uniformly. You often end up with a wider mix of chain lengths. For measuring this distribution, we turn to chromatography, specifically gel permeation chromatography, GPC, which is also known as size exclusion chromatography, SEC.
GPC or SEC. Okay, what does it do?
GPC physically separates the polymer molecules in a solution based on their size as they pass through a column packed with porous gel. Bigger molecules come out faster, smaller ones take longer detours through the pores.
So it sorts the chains by length.
Exactly. This allows GPC to provide not just the average molecular weight, MW, but crucially, the distribution of molecular weights. This distribution is often quantified by something called the polydispersity index, or PDI.
Polydispersity index, PDI. Help our listener understand what that means in practical terms. Why should they care about PDI?
Think of it like this. PDI measures how uniform the polymer chain lengths are in the sample. A PDI value close to 1 means all the chains are very nearly the same length that's highly uniform, or monodisperse.
Okay.
A high PDI, maybe 2 or 3 or more, means you have a broad mix, some very short chains, some medium, some very long chains. It's like trying to build something strong using pieces of wood that are all wildly different lengths.
That randomness creates weak points.
Precisely. A high PDI generally leads to poorer mechanical properties, like lower strength or toughness, because the short chains act as defects. GPC measurement ensures the RPT has a low, controlled PDI, meaning the chains are relatively uniform in length, which is essential for consistent, predictable, and strong material performance.
Okay, that makes sense. And finally, one more technique mentioned, X-ray diffractometry. What does that add to the picture?
X-ray diffractometry, often using techniques like SAX-XS, small-angle X-ray scattering, and WXS, wide-angle X-ray scattering, is the ultimate non-destructive way to probe the internal structure at the nanoscale.
Non-destructive blueprint.
Kind of. By shining X-rays through the fiber or material and analyzing how they are scattered or diffracted by the atoms and molecules, you get detailed information about the internal organization. This includes a precise measurement of the degree of crystallinity, the size and arrangement of crystalline regions, the orientation we talked about earlier, and even subtle differences in molecular configuration or packing, like identifying different crystalline forms, sometimes called alpha and beta forms in polymers.
So it gives you the full architectural plan of the inside of the fiber.
A very detailed one, yes.
Yeah.
All these state-of-the-art analytical tools, FOR, SEM, FTIR, NMR, TGA, DSC, GPC, X-ray used in combination, are absolutely necessary. They provide the comprehensive characterization needed to ensure that recycled fiber meets the stringent quality requirements demanded by today's high-performance industries and to verify that it truly is recycled content.
That is an immense technical investment, a whole suite of advanced analytical chemistry and physics, just to verify the purity and performance of what started as a humble recycled water bottle. It truly underscores the complexity involved in genuinely transitioning away from the perhaps deceptive convenience of just using virgin materials all the time.
It absolutely does. It's not simple. And this complexity, this need for proof and verification, brings us naturally to Section 6, the larger implications. How does all this science fit into the bigger picture of the circular economy, moving from a linear take, make, dispose model to one of perpetual reuse?
Right. Our sources were very clear that the ultimate goal here isn't just recycling more plastic. It's about a fundamental shift in how we do business, moving towards sustainable business models, and ideally, the holy grail of closed-loop business models.
Closed loop, meaning indefinite, high-quality recycling without significant material degradation over cycles.
That's the ideal, yes. Keeping the material in use at its highest value for as long as possible.
And within that, we need to be careful with our terminology, ensure we're using it correctly. We've talked about upcycling.
Which is converting waste into a higher level application, right? Like the PET bottle becoming that high performance, high tenacity yarn we discussed. That adds value.
Exactly. The opposite then is downcycling. That's when you convert high-quality waste material into something of inherently lower quality or performance. Using mixed, contaminated textile waste for simple automotive insulation or carpet backing, for example.
And the push in the modern textile and packaging industry is aggressively towards maximizing upcycling and perfecting those closed-loop systems where possible.
That's the direction of travel, definitely.
But in a global supply chain that's notoriously complex and frankly often opaque, there are huge opportunities for greenwashing, claiming something is recycled when it isn't, or exaggerating the content. Credibility seems paramount. How can a consumer, or maybe more importantly, a massive global brand sourcing materials, actually trust that the recycled content is real, traceable, and was handled responsibly?
That is the million-dollar question, isn't it? And the answer largely lies in robust, independent, third-party certification bodies and standards. They provide that essential layer of verification and accountability that the science alone can't guarantee across the whole chain.
Okay, so certifications are key. The sources highlighted 3 main ones. Can you break those down for us?
Sure. First, there's the Global Recycle Standard, or GRS. This one is pretty comprehensive.
What does GRS verify?
It verifies the actual percentage of recycled material in a final product, distinguishing between pre-consumer, industrial scrap, and post-consumer, like our water bottles waste. But it goes beyond just content. It also sets stringent environmental processing criteria for the factories, involve things like chemical use restrictions, water treatment, energy use, and includes social responsibility requirements as well.
So GRS is content plus responsible production. What's next?
Then there is the Recycled Claim Standard, or RCS. The RCS focuses primarily on tracking the recycled material itself.
Tracking it how?
It acts as a crucial chain of custody verification system. It tracks both virgin and recycled input materials right through the supply chain, from the recycler to the final product. It often works in tandem with another standard called the Content Claim Standard, CCS, to meticulously verify the exact recycled input percentage and ensure it hasn't been diluted or substituted along the way.
So RCS is about traceability and validating the claim. And the third one mentioned?
The third one highlighted was cradle-to-cradle certification. CDC takes a slightly different, perhaps more holistic approach.
How so?
Cradle-to-cradle certifies products based on multiple sustainability factors, including material health, ensuring materials are safe for humans and the environment, material reutilization, designing for easy recycling or composting, renewable energy use, water stewardship, and social fairness. The key focus for our discussion is its emphasis on designing products specifically for safe and effective material reutilization at the end of their first life.
So these certifications, GRS, RCS, CDC, they're the tools brands and consumers can use to navigate the claims and build trust in recycled products.
They are essential tools for transparency and credibility in this market, yes.
Okay, let's try to bring all these intricate layers, the chemistry, the physics, the engineering, the economics, the certifications back to the surface. Let's summarize the key takeaways from this deep dive into recycled polyester. What should our listeners remember?
All right, key takeaways. First, I think we clearly established that shifting aggressively towards rPET offers significant, measurable environmental benefits, primarily by slashing reliance on virgin petroleum and drastically reducing the greenhouse gas emissions associated with new polymer production, and critically helping tackle that horrific microplastic pollution linked to virgin synthetic textiles.
Okay, environmental win.
Second, the quality question. We saw compelling evidence that high-quality rPET produced using advanced methods can achieve comparable and in some specific functional areas like acoustics or even certain mechanical strengths potentially superior properties compared to virgin polyester. It's not automatically an inferior substitute.
Got it. Quality can be excellent. Third takeaway.
Third, the vital role of advanced analytical tools. Things like TGA, GPC, NMR, DSC. They aren't just academic instruments. They are absolutely critical, non-negotiable tools for ensuring the quality, purity, and consistency of rPET in the real world, especially for guarding against common, potentially harmful contaminants like acetaldehyde. These tests are the gatekeepers of the closed loop.
Testing is paramount. And finally,
and perhaps the most significant research breakthrough we discussed, that specific melt spinning study proved that bottle-grade recycled copolymer PG, the rPETB, can successfully substitute for standard fiber-grade virgin PET in industrial processes, producing fibers with equivalent high performance, even though it achieved its strength through a different mechanism, molecular orientation versus crystallinity.
That's the scientific proof that a high-performance closed-loop system using post-consumer waste is technically feasible today.
It strongly suggests it is, yes.
So, the science seems to be there. The researchers have provided the characterization tools, the processing insights, even predictive models. But the sources repeatedly hinted that the biggest hurdle now isn't necessarily the lab work. It's scaling up. It's implementation. It's getting it from the factory floor to the consumer reliably.
And that leads perfectly into my final provocative thought for you, for our listeners, to mull over. The primary future challenge, it seems, lies not only in continued technological advancements, although those are needed, like automating the sorting of complex textile waste, or developing truly effective systems to recycle blended fabrics like polycotton.
Which are notoriously difficult.
Extremely. But perhaps the bigger challenge now is closing the persistent gap between this advanced scientific knowledge and its practical, widespread, verified implementation. How do we ensure that these sophisticated recycling processes and the strict traceability systems, like GRS and RCS, are actually adopted and function accurately across a fragmented, often opaque, intensely cost-competitive global supply chain?
And how do we promote genuine consumer awareness and trust effectively enough to drive mass market demand for verified recycled products, maybe even at a slight premium?
Exactly. That implementation gap, that chasm between the proven potential and the on-the-ground reality. Bridging that feels like the next Everest for the global textile and packaging industries to climb.
A perfect thought to end on. The science says the bottle is ready to become a breakthrough fiber. Now the global system just needs to catch up and make it happen reliably. Thank you. This was a fascinating deep dive.
Always a pleasure. A lot to think about there.